Yeah. So I extended the title to include American options and dynamic risk measures. In fact, Leo asked me last time, now tell me about American options, because so far I had only mentioned European options. So I will say something about American options, and actually there is a connection to the second topic. Now for American options, we are going to look at the situation from the point of view of a buyer of an American option who is confronted with the problem of optimal stopping. That's a very classical chapter on probability. We are going to look at that and also at some robust extension. And then we are going to take the point of view of the seller who is interested in pricing and hedging such an instrument, both in a complete and an incomplete setting. And the mathematics needed in this context is related to the problem of time consistency of dynamic risk measures. And so this will lead us to the second part, where we also will focus on law invariance for dynamic risk measures. And we are going to look at the situation on a Brownian filtration, and I'll shortly sketch the connection to backward stochastic differential equation, which on the analytical side is related to certain nonlinear PDEs. Now first we'll just take the simplest case of discrete time, in order not to have to worry about certain technicalities. And an American option means that at each time t, you have a certain payoff profile. And if you have bought that option, you can decide which time you are going to choose to exercise that option. And if you decide to take little t, you're going to get paid ht of omega. So ht depends on scenarios. So the buyer can exercise the option at any time between 0 and t, which is a stopping time in the technical sense. And the qualitative meaning is it should not anticipate future developments. So the technical condition is here, and here are two examples of stopping times, random times. And the first is a bona fide stopping time. You fix a level C and you decide to stop or to sell as soon, or to exercise that option, as soon as the value of your payoff process exceeds the level C. So that's, in this technical sense, a stopping time. The random time, which gives you the moment where the maximum is reached over the whole time interval up to big T, that is not a stopping time. We had that already before on some transparency, because at that moment, in order to be sure that this is the maximum, you would have to know already the future development, which of course you don't know. So this kind of thing is excluded.
What is known and what is unknown? HT is known?
You know, the contract in principle specifies, if you are going to stop at time t, I can tell you already now what you're going to get if the underlying cause does this and that. So more specifically, if you take an American version of a call option on the underlying stock price fluctuation xt, then the contract says, and if C is the exercise price, if you exercise at this time, then you get, depending on what the underlying stock price will be, the positive difference, the positive part of the difference to the exercise price. But of course, you don't know in advance what these prices will be.
So in this case, this will serve as your HT?
Yes, yes. So that's a specific example of HT of omega. We had this before, but before we only looked at this profile at the terminal time, but now it's available to you at any time, and you decide at which moment you want to exercise. so the buyer of the option now uses some probabilistic model. So let's say the probability measure P, which we wrote down to begin with, and he wants to maximize the expected payoff. So he wants to choose, this should be a stopping time, tau, such that this expectation is maximum. That's a classical problem. It's well known how the solution works here in discrete time. You use so-called Snell's envelope, which is the smallest super martingale above your payoff process. And there is an immediate recursive construction. At the end, you take the final value at the final time, and then working yourself back, your way backwards, at each time you take the maximum of the present value. This is what you could get if you would exercise right now. If you would decide to wait, then, and if you know already what your position would be worth one step further, you would have this quantity, and you compare the expectation of the value one step further if you wait with this quantity which you could get right now by exercising now. And ut is the maximum of these two quantities. Now in particular we have ut bigger than or equal to this conditional expectation. That's a super martingale property. Any such super martingale can be decomposed into a martingale minus some predictable increasing process. And the optimal stopping problem for the buyer is solved, for example, by the first time where this Snell envelope touches the underlying payoff process. So that's optimal in the sense that the expectation of the payoff at that time is maximal. It's in general not the only one. For example, this time is also optimal. It's the last time where the process still has behaved like a martingale, this value process. At the next step, this process A will pick up, and this process A destroys, when it becomes non-zero, the martingale property. So here the rule is stop as soon as Snell's envelope loses the martingale property. And the characterization of optimal times is that tau is optimal if and only if you touch at that moment and you have not waited too long. So tau lies between these two stopping times, and in that sense this is the minimal optimal stopping time and this is the maximal optimal stopping time. Now in the Markovian case, where you have some underlying Markov process, where the payoff profile is defined in terms of that underlying Markov process, for example, as a function of the underlying price process, then the Snell envelope also has a Markovian structure. It's a space-time function of price and time. And you have then in space-time a certain region, the continuation region, where this is strictly bigger than what you could get right away. And this is a region where you let it run. And you stop by this recipe as soon as you leave the continuation region. Up to that time, so as a function on that continuation region, u is a martingale along the price fluctuation, which for the Markov process has an analytical description, space-time harmonic. If this is a nice diffusion, it would be a solution of a PDE, and you have a free boundary value problem of Stefan's type to solve that.
Do you assume any type of complete Markov?
Hmm?
Do you assume complete Markov?
I will come, no. This optimal,
What is the expectation under what probability measure?
the subjective expectation of the guy who holds the option. So he can choose a model and then can solve this problem. We come now to completeness. From the point of view of the seller, the situation is different. The seller wants to hedge, wants to prepare for the moment when the buyer exercises. Now we take the financial market story, which we had in the first lecture. So we have a d-dimensional process of asset prices. We assume that the model is arbitrage-free. So there exist equivalent martingale measures. And the simple complete case means there's exactly one equivalent martingale measure. Now for the seller, the question is which capital is needed at each time to hedge against any exercise time which comes afterwards. And here we have a recursive structure. At the end, of course, he just needs this. At any previous time, if we know already what he will need one step further, well, either he needs this in case the buyer exercises now, then he needs that amount. If not, then one step further he needs this amount, which has already been computed recursively. And in order to implement, to generate this amount by a trading strategy on the financial market, the complete case, this is given by the conditional expectation under the equivalent martingale measure. But we see it's exactly as before. It's the structure of a Snell envelope. So this successive capital needed to hedge is simply Snell's envelope of the payoff process, but now with respect to the martingale measure, P star. If we compare it to the associated European option, where exercise is only allowed at the final time, big T, then this would be the unique arbitrage-free price at time T. And this, by the super martingale property of the Snell envelope, is always above. It would be equal if we would happen to have this property under the equivalent martingale measure. For example, if HT is a sub-martingale under P star. One example is the American call option of that type. Say a call option on the ith asset. XT is a vector of the asset prices. Now, all the arguments are in terms of the discounted quantities. So with a fixed interest rate, the discounted payoff profile would look like this. And then, since this is a martingale under the equivalent martingale measure, by Jensen's inequality, since we are applying here a convex function, we would have indeed the sub-martingale property for the American call option, and the pricing problem is already solved in this case. For the put option, it's different, and in general, it's different, and in particular, it's different if now we switch to the incomplete case. So in the incomplete situation, we have more than one, and hence infinitely many equivalent martingale measures. And so the question is, what is now, from the point of view of the seller, an arbitrage-free price for that American option? For a fixed exercise time, we could treat, supposing for the moment that the exercise time is already known, then we could treat it as an European option, this random variable here. And there, the set of arbitrage prices is simply everything which you could get as an expected value under some equivalent martingale measures. So these are all arbitrage-free prices for the European option H exercised at this fixed stopping time tau. Now what do I mean by an arbitrage-free price? I mean any price which you would charge such that the extended model, where the option is now part of your financial market, it's a liquid instrument now on the market, together with that price, it creates an extended market model which is arbitrage-free in the sense that in that extended model there exist equivalent martingale measures. And that's a theorem that in that sense, the prices which are arbitrage-free in that sense are exactly those here. Now what do we do for the American option? Let's take the following definition. We say that P is an arbitrage-free price for the American option if in the first place P is not too high, in the sense that there is some way of exercising such that P is not above at least some arbitrage-free price, no, for the European option corresponding to that stopping time. And P is not too low in the sense that there is no exercise time such that the present price would be strictly below any arbitrage-free price for that European option. And then the theorem is that the class of all arbitrage-free prices for the American option is an interval with these endpoints here. So here you take the solution of the optimal stopping problem for the martingale measure P star, and you take here the inf, and here, well, I claim, part of the theorem states, you can interchange, and this is useful for some purposes. And the upper interval is the soup of the values of the optimal stopping problems over all equivalent martingale measures. Now either this American option we are considering happens to have a unique arbitrage-free price. For example, if the situation is complete, then of course here these two limits coincide and the interval reduces to 1 point, because then there is only one equivalent martingale measure, and clearly these two quantities coincide. And in that case, there exists a strategy for the seller which hedges in this sense, and which is best in the sense that he really also touches for some exercise time tau of the buyer. Or the upper limit itself is not an arbitrage-free price, does not belong to that set. Now the hedging problem for the seller can be discussed in terms of super hedging, which I shortly explained in the first lecture. And here this interchange is related to a certain property of the set of the equivalent martingale measures, and this plays a role in an extension of the theory of the Snell envelope, namely for lower Snell envelopes. And this we now discuss in greater generality. So let's take some class of probability measures which are equivalent to well, the reference measure P. This class is stable or stable under pasting if you can do the following. You take any two models, any two probability measures Q1, Q2, and you take any stopping time. Up to that stopping time, you use model number 1, and then you switch into to model number 2. Now what does that mean? For any A, you first take the conditional probability in that second model of A given the information up to time tau, and then you take the expectation under the first model, Q1. So this, the pasting of Q1 and Q2 at the stopping time tau. And stability by definition means that if you do that construction, you get again a model in the class Q. And the class of martingale measures is stable in that sense, very easy to see. If we take the pasting of two equivalent martingale measures at some stopping time, I claim this again is a martingale measure. Now to show that it's a martingale measure, it's enough to show that the stopping theorem holds for any stopping time. So we take some other stopping time sigma, and we want to check that this is equal to here the final point. And that would mean the stopping theorem holds under P star. Now by construction of the pasting, this looks like this. Now P2 star is a martingale measure, so on the set where sigma is smaller than tau, this is, yeah, this has nothing to do with martingale, this simply, because then x sigma is already measurable on that set, so you don't have to predict it. Or now by the martingale property, if tau comes what am I doing here? No, the other way around. If sigma is bigger than tau, then by the martingale property, this is equal to x tau. So putting it together, we have this. This is some new stopping time, but the first measure is a martingale measure, so here the stopping theorem holds. And at time 0 anyway, p star coincides with p1 star, so that's a proof of stability. Now we can formulate a robust stopping problem, where the problem now is formulated in this way. Maximize over all measures in some class, Q, which we assume to be stable, the expectation, and find a stopping time which maximizes this inf. For example, if we take the Gilboa-Schmeidler preference framework, which I sketched last time, we could even throw in a utility function, apply it to the monetary result, define this process, and then there would be a preference of Gilboa-Schmeidler type, and we would have formulated a stopping problem with respect to such robust preferences. Now the solution of this problem is via the lower Snell envelope. So here we do the following. For each fixed model Q, we have the standard theory of the Snell envelope. Now here we take the infimum over all measures in that class. So here I spelled it out. And now one can show that here we can interchange. And in particular, at this point, stability is needed to prove this sort of interchange. And in particular, at time 0, we get, and if we take specifically the class Q of equivalent martingale measures, then that's the interchange which appeared earlier. Now, in general, for this robust stopping problem, this is now the value, and the solution of the optimal stopping problem in its robust version is, as in the simple case, given by the first, or a solution is given by the first moment where the lower Snell envelope touches the payoff process. Now, at this point, some connection to dynamic risk measures appears. And to see that, have a first look at that, even though we haven't systematically started to discuss dynamic risk measures yet. We look, in analogy, at the upper Snell envelope. So the upper Snell envelope with respect to such a class is this, and here clearly we could exchange, so that's a soup over all Q's also of the values of the optimal stopping problem for a fixed Q. Now if Q is stable, then we can verify a recursive construction. So at the end we start with the final payoff. And then at each time, as before, we look here at conditional expectations, but it's a soup over all Q in our class of models and compare it to the payoff which we could get right now. Now,
so what does it mean?
I claim that the process which is defined up there can also be identified by this recursive procedure.
But you say use stable, if use stable.
Is equal to HT? No, I don't get the
You
question.
write use stable, then
Yeah, then it's true. In order to prove, starting with the definition.
What is the definition of stability?
That two models in the class Q can be pasted together at any stopping time. Now, in the special European case, which would correspond to the case HT is 0, you don't get anything before, only at the final time. This reduces, then it reduces to this quantity, and you get this relation. Now this is like a robust martingale property. This would be the martingale property for a fixed measure. So it's a martingale property in this robust form. And this is exactly time consistency of dynamic risk measures, as we are going to see next. So now we start from scratch and look at dynamic risk measures. So we have a probability space and we have a filtration. Financial positions, as before, as are described, the net discounted result is a random variable FT measurable. We assume bounded to avoid certain integrability problems, which that's a separate story to do the extension. So let's denote by script xt the class of bounded random variables which are FT measurable, so observable up to time t. Now for a fixed time, we say we have a convex risk measure conditional on the information up to time t, if for each financial position, rho t associates some numerical value, some monetary requirement, but this will now not be a constant. It will depend on the information up to time t. So it will be a FT measurable random variable. And then, as in the static case, we have here a monotonicity requirement. If x is, p almost surely, always better than y, then we need less reserve. The capital requirement is below the capital requirement for y. We need cache invariance as before, now not only for constants, but also for amounts which may depend on the information up to time t. And if we add that amount, then it changes the original risk assessment in this way. It reduces the capital requirement exactly by that amount. And we have a convexity condition as before, but now also in a conditional sense. Here this lambda, the convex combination, may depend on the information up to time t. And sometimes, for convenience, we are going also to assume that it's normalized to rho t of 0 equal to 0. Yeah?
How is it different from applying standard risk measure pointwise?
Yeah, it's a technical thing. It's like.
Is it different from applying standard
No. When you can, but if you start pointwise and say for each omega now I take a risk measure, but then you want to work with it, so it has to be measurable, and so you must.
Point in time.
At each point in time.
But it is measurable, just by definition of standard risk measure.
No, I mean, for a fixed omega, you could now define a static risk measure, right? But in order so that you do this for every omega, so that the result fits together in a measurable way, you must do something. I mean, it's just a technical little thing. So here in the definition, we do it right away by requiring measurability. Okay, so that's a dynamic risk measure. Now we apply, essentially, of course, we do that. We apply the previous discussion for static risk measures now to these things. So the Fatou property, in this sense, here, something is missing. If you have a kind of Fatou lemma for these risk measures, so here there should be rho t of xn, then in this case we get a robust representation in analogy to the static case, now in this form. So the philosophy is the same as before in the static case. Here you compute a conditional expected loss. You take the worst case over all measures which are in this class. This is a class of measures which are absolutely continuous with respect to p. But you take them seriously to different degrees. This is given by alpha t of q. And alpha t of q is itself ft measurable. It depends on the information up to time t. And you can define it as essential soup of the conditional losses over positions which are acceptable in the light of the risk measure up to time t, where the exception set is now the class of all financial positions which do not require a positive cache addition at time t, in the sense that rho t of x is almost surely non-positive. And once you have the acceptance set, you get back the risk measure by taking the smallest amount which makes a given position acceptable. So the previous story,
This is at time t or starting from time?
at time t. At time t. So this is a class, the acceptance set, I should write, at time t. So that at time t you reassess the situation.
Yeah, you look
Forward, yeah.
starting from time
Forward.
t.
Yeah, right. From time t on, one should say. Right. Because here we are looking at positions always at the final time. We could also now apply this whole thing to processes instead of random variables at the final time, but I'm not going to go into that. So here is an example. The entropic risk measure, now in conditional form. You fix some constant beta, and you take here the log of the conditional expectation of the loss weighted by some exponential loss function, and that's the conditional entropic risk measure at time t. The corresponding penalty function now is the remaining relative entropy from time t on. So what do? At time t, you take the conditional distribution on future, given the information up to time t, you compare for the two models Q and P, you take the relative entropy, and that is the penalty function for the entropic risk measure. Now in this case, you see directly time consistency in the following form. The capital requirement now for the position x is identical to the following. Here, this is a quantity, the capital requirement one step later. So you could say, okay, one step later I will have to produce this capital requirement. So as a position, it's minus this. So I might as well just look one step ahead, if I know already this quantity, and take the capital requirement to make this acceptable. So this identity is one definition of time consistency. And here it holds, as one can check directly. So you apply rho t to this quantity. Yeah, now if we spell out rho t, you have to take the logarithm, and here's some conditional expectation. And this gives us exactly that, and now by projectivity of the conditional expectation, it reduces to this, and that's exactly rho t of x. So here we see a notion of time consistency, and we see that it's verified by the entropic risk measure. So now, in general, for a dynamic convex risk measure, we will say that it's time consistent. Yeah. This was the property, this recursive property was the one we just had, or equivalent, this is equivalent to the fact that if at the next time the capital requirement is the same for two positions, then it should also be the same capital requirement at the present time t. Now this implies, but it's not necessarily equivalent, to the following condition. Here you say, what will be acceptable at the next time should already be acceptable now. If I'm sure that one step later I will find that position acceptable no matter what has happened in that period, there's no reason that I should not accept it as a present time. Okay, so it's easy to see that these two are equivalent, and that yeah.
Can you just explain this for line of one? Assuming x is the position where I have a stock which is going to pay me a dividend between t and
Excuse me, once again, sorry,
Yeah.
I got lost.
Assume x
Yes.
in a share, in stock,
Yes.
which is going to pay me a dividend tomorrow.
Yes.
Between now and t plus 1. The size of the dividend is $1.
Yeah.
And Y is a very similar stock which is not going to pay a dividend. After the dividend is going to be paid, they're going to be completely equivalent. So rho t plus 1 of x is identical to rho t plus 1 of y. But meanwhile, today, I need much less capital, $1 less capital, for x than for y. In this case, the first equality will not apply to the second equality.
Yeah, okay, but I think we have now switched the discussion already to stochastic processes, to a time schedule, what happens with the position. In this discussion, we simply stick to final payoffs at the final time. So if we bring in dividend payments on the way, we look already at the time schedule, so at the stochastic process which we want to assess, and then anyway we have to modify the story. Okay, now let's take a dynamic coherent risk measure where we have some class of models, and at each time we use with the same class Q this risk measure, this coherent risk measure induced by that class, conditionally, by using conditional expectation. Then, even though we use here the same class already all the time, it's not necessarily time consistent. And one can show it's time consistent if and only if the set Q is stable, which was shown in the paper by Arznel, Delbin, Hébert, Heath, and Q. But here we have already seen it. This was the argument which came out of the upper Snell envelope. So this would be a corollary to our discussion of the upper Snell envelope. Now, how does this extend, this stability story here, now to dynamic convex risk measures? Dynamic convex risk measures are given by their corresponding penalty function. So for each measure Q, which is absolutely continuous with respect to P, we have this process alpha T of Q. And the question is how is time consistency of the risk measure characterized in terms of these processes? Now here is a characterization, some kind of Bellman principle, which comes in here. It's time consistent if and only if for each position and for each model Q, the risk process plus here the penalty process form a Q supermartingale. Now it's easy to see that this condition is sufficient for time consistency. So let's check time consistency in the following form. I had written it down as a condition. If this is equal, then this should be equal, but an equivalent formulation would be if I have an inequality here, so I also get an inequality here. Now how do I get it? I take this. Supermartingale property says this is above the conditional expectation of that combined process one step later. Now I use the assumption that rho t plus 1 of y is above rho t plus 1 of x. I plug it in. Now, by the robust representation theorem for the risk measure here, we know for each x this here and each q, this is above this thing minus this. So the sum is above this. So I plug it in. But now I have, by iteration, by the projectivity of conditional expectations, I obtain this. And, but the soup of, so I get rho t of y is bigger than or equal to this minus alpha t of q. Again, by the robust representation theorem, the soup, the essential soup of these quantities will be this. And since these approximating terms are below all the time, we get the desired inequality. So this direction is easy. What is a little bit harder is the converse. So in order to prove the converse, we do the following. Here we look just one step ahead. So these are positions which, where the outcome will be known one step later, measurable with respect to ft plus 1, and which are acceptable. And I define alpha t just one step ahead as a corresponding penalty function if I take the sup not over all, not over all acceptable positions, but over this class. So here that's wrong. I should write this class here. And then there is a lemma, and that's the hard part of the proof, to show that time consistency implies this relation for the penalty functions. So the penalty function now is the penalty function, the myopic penalty function, just looking one step ahead, plus a conditional expectation of what the penalty function will do at the next time. Illustration for the entropic risk measure. It's a formula for the remaining entropy, which in the case of entropy you can just explicitly compute. It's the entropy looking just one step ahead. If you compare these measures just on the sigma algebra up to time t plus 1, but not over the full horizon, plus the conditional expectation of the relative entropy computed one step later. And this structure is inherited by the general penalty functions in this story exactly under the condition of time consistency. Yeah, and using that lemma, we can show that this Bellman principle holds, verify that for any Q, this combined process is a Q super martingale. Yeah, by the lemma, we can rewrite the conditional expectation of this as a difference of these terms, and then pulling these terms together, we get this estimate here, and by time consistency, we can replace it by this. And this is exactly the Q super martingale property for the combined process. Yeah, illustration of the Bellman principle for the entropic risk measure. Here I can compute explicitly. It's this plus the remaining entropy, the remaining relative entropy. Now, to deal with this, I introduce one fixed measure, Qx, where I use the position we are talking about here to define a density, a radionuclidium density with respect to P. And then by the properties of relative entropy, this is equal to the relative entropy of Q with respect to that intermediate model plus a conditional expectation here of the log of the density, which gives me these terms. So this cancels, and I get this martingale. And here I get the process of remaining entropies between Q and Qx. And this will be a super martingale going down to 0, so potential in the jargon of martingale theory. And the whole thing is a Q martingale if and only if this term drops out. And that means if and only if Q is exactly this worst case measure Qx, worst case for the position x, where I'm right now testing the super martingale property. Okay, so that's time consistency for convex risk measures. Now, one other aspect. Let's now focus on the special case of law invariance. So this is part of the dissertation which was just finished by Stefan Weber in Berlin, which is going to, and this part is going to appear in Mathematical Finance. First, the static case. Now, there we have looked at distribution invariant or law invariant risk measures. Remember, risk measure is called law invariant if it only depends on the distribution of the financial position viewed as a random variable on the probability space with P. And so I could say the risk measure is actually a functional just on the distributions which arise. So I can write it in this form for some functional on the space of probability measures on the real line with compact support, because we are talking about bounded random variables. Now the monotonicity requirement of the underlying risk measure translates the monotonicity with respect to stochastic dominance of R, big R. Cache invariance has to do here with translations of the distribution, and the simple Lipschitz continuity estimate now is formulated with respect to the Wasserstein distance between the two probability measures with respect to the supremum norm. So it's the infimum of the L infinity norm over all random variables x and y, such that x has distribution mu and y has distribution nu. So we can shift everything now to these functionals on lotteries, on probability distributions, and in particular we can define an acceptance or a rejection set on the level of distributions. So N is the acceptance sets, where I don't need any cache to add any cache to make it look good. Now here, if I take a convex combination, either in the acceptance set or the rejection set, how can I view that? A convex combination is such a thing. This I can view as a compound lottery in the economical jargon. So it's a lottery in two stages. First, I throw a coin with bias lambda to decide which lottery I'm going to have. And then if in both cases the result will be acceptable, why not then accept also this compound lottery? That would be a convexity property of the set N. And it's equally plausible, to some extent at least, to say that the same thing for the rejection set. If I do this compound lottery, I flip my coin, and then if I know in both cases I will arrive at a lottery which is not acceptable, why should I accept it now? Now, if we introduce this condition and some technical assumptions, then one can show that the acceptance set must be of that type with respect to some loss function little l, and that means I am down to a risk measure which is of the type expected loss. More precisely, if I also just consider convex risk measures, then this loss function will indeed be convex, and it will be exactly the risk measure of shortfall risk. So this is a characterization of shortfall risk with respect to certain convexity properties on the level of the functional, viewed as a functional on lotteries. Now the dynamic case. Now here I have written it for a change with explicit use of the term structure of interest rates. So far we don't see it because we have always discounted it, but now let's bring it out. So we have zero coupon bonds, price at time little t is BT big T for a zero coupon bond, which will pay face value 1 at the maturity big T. If we spell it out this way, cache invariance for the non-discounted quantities would look like this. If I add some amount, which then is invested in a zero coupon bond with maturity T, and if I invest this amount, this will accrue to the final payment M, then I can no, if now I invest M and the final thing will be this, and then I can withdraw exactly this amount. So cache invariance takes this form. And now if I take dynamic monetary risk measures, I say in the dynamic case, I call them law invariant. If at each time the risk assessment depends only on the conditional law of x and y, given the information up to time t under our reference measure p. And then rho t of x takes this form. Here, this factor is the price of the zero coupon bond. And here is some risk measure on lotteries as above, with certain acceptance and rejection sets. And now, I say, these are acceptance consistent. If something which will be acceptable at a later time, a distribution which will look acceptable to me tomorrow, should also look acceptable to me, and the same here. And if I have both conditions, it simply means then that these acceptance sets are actually stationary, are the same, and that means I have one fixed functional here on lotteries. And in this case, my risk measure has this structure, price of a zero coupon bond multiplied with this functional applied to the conditional distribution of x. Moreover, the consistency conditions imply now convexity. And by the above arguments in the static case, R must be the shortfall risk measure for some convex loss function L. And so this is one line of argument which singles out one specific choice for a dynamic risk measure, namely a shortfall risk measure applied in this way. Okay, that's one other aspect of time consistency which was used here in the sense of acceptance and rejection consistency. Now finally, in the final minutes, I've made a point of staying very simple, just discrete time. But now let's show some connection to more to activities with a more analytical flavor, and in particular some nonlinear PDEs. Suppose now that we develop this story on a Brownian filtration. And then very naturally there is a link to backward stochastic differential equation, and that means also to certain nonlinear PDEs. So let's fix a Brownian motion or a Wiener process on some probability space. And Ft is the filtration which is induced by that Brownian motion, so just the observation, the information we get by observing the Brownian motion. Yeah, what does it mean, a backward stochastic differential equation? It's more complicated than just, with a deterministic equation, just looking the other way. It's really different now, in the following sense. You have here a final condition, but you can't observe it at the beginning. This will only be revealed at the end. And you want to solve a stochastic equation of this type, driven by Brownian motion here, with some volatility which you have to construct, which is part of the solution. And it's driven here by a function little f, which in principle may depend on yt, on zt, t, and here it may also be actually a process, not just a function, may depend on scenarios. Okay, so the problem is find adapted process yt and zt such that in the end you will get h, and so that the dynamics is described by this. And there is literature on these backward stochastic differential equation, which was started by Pardu and Peng, then Peng and many others. In particular, under Lipschitz conditions, you get existence and uniqueness of solutions. And I just show you, a connection to nonlinear PDEs. Suppose we have a nice diffusion process with generator L, and that H is a function of the terminal value of your diffusion, and F is a function, so no randomness here. Then we make the ansatz that yt is a function of the present position of your diffusion process and the time. And then by Ito, the dynamics here would look like this: the gradient of u in the space variable dw plus the diffusion operator here plus time derivative applied to u dt. And you are looking for a solution of this equation. So in particular, this implies that this term here must be equal to this, And this means that you must solve a certain nonlinear equation here with this terminal condition big T. And once you have that, the Z here is simply given by the gradient in the space variable of your solution of the nonlinear PDE. Now, probabilistically, just to see a little bit the flavor, in some very simple cases, but they don't have to be Markovian. For example, here, a simple linear function in Z, but with a coefficient which may be any adapted, well, reasonably bounded adapted process. Then the equation we want to solve can be written in this way. This we can view, this process here, the difference, we can view as a new Wiener process under a Girsanov type change of measure. And then we simply take under that new measure, which comes up via the Girsanov transformation, the conditional expectation of H. By Ito's representation theorem, this can be written as a stochastic integral. And that means that, that it solves this quantity here, this process here solves the equation. Yeah, and there are other simple examples which all fall under the general existence and uniqueness theorem under Lipschitz conditions. Now I show you an example which does not fall under the standard Lipschitz condition. I take the square. But we can solve it easily, and it's actually our entropic risk measure. Our entropic risk measure. If we write down this, it turns out it solves this backward stochastic differential equation. Very easy. First we consider this, apply Ito's representation theorem. Then we apply Ito's formula to y, which is a logarithm of ut. By Ito's formula we get this. We plug in what we know about u, and we realize it does solve the equation with zt equal to phi t over ut. Yeah, and in this example we can of course also illustrate the general structure which we had seen before. The remaining relative entropy can now be computed very explicitly. The super martingale properties we had, the martingale property of the worst case measure, so all this comes out very explicitly now in this setting, but I'm not going to dwell on that. Just in general now. So Peng in particular recently has proposed to define, whenever you have a solution of a backward stochastic differential equation driven by some function f with terminal condition, and we take the solution here, let's view that as a certain nonlinear conditional expectation of h with respect to the information ft. Now if you look, if you do have a solution here of such a backward stochastic differential equation, you see immediately that you get time consistency. If f, the driver function, does not depend on y, we get Cache invariance. And if f is convex in y, we get a convexity property. And all this means that up to a sign, we get time consistent dynamic convex risk measures. Now, if we plug in here a minus sign, it fits exactly the framework. Now, the converse. So a paper of Peng, which is going to appear probably in the Zeitschrift for Probability Theory and Related Fields, says that under certain boundedness assumptions, such nonlinear conditional expectations, respectively risk measures, on a Brownian filtration must be solutions of some backward stochastic differential equation, thereby be related to some nonlinear PDE. But that's not yet the final word, because the boundedness conditions are such that the entropic case, which falls out so easily, is not covered. So it shows there is room for extensions and improvement also at that interface. Okay, and that's what I wanted to explain today. Yeah.
Something. These are always, what happens is that what you get is always a pure Cauchy problem, right?
Yeah.
That is somehow you assume that the variable, I'm talking as a differential equations.
Yeah.
You never apply boundary conditions. There is no sense for boundary conditions in this case.
No, I have not.
Because in differential equations, the boundary conditions make a lot of difference. For example, if you take a heat equation or a similar, you don't have the expansion to infinity, so instead you have blowups. So
No, I have not yet looked. Anyway, I have not really. I wanted to show it just for people who are interested in these. And I have not really worked much myself, except by looking at the entropic example in connection with the work of Peng. So I have not yet looked at such situations, but I wouldn't be surprised if there is a natural way of motivating such additional constraints. So some.
Well, what is the natural analogy? I mean, your space variable. Once you translate into differential equation, what is x, the variable x in this case?
X could be a model for the underlying financial market.
Which means maybe it has to
so
be
a vector of asset prices.
But positive almost?
Yeah.
So
yeah.
right there you get
Okay, that we would have immediately, that's true. Yeah. And
like an American option, you must exercise as soon as it's high enough, then you get
yeah.
I know from another field, for example, Navier-Stokes equations,
yes.
where people in probability theory are trying to get, for example, in bounded domains. And then they have lots of difficulties translating into probabilistic terms the boundary conditions. I know terminology like branching processes, things like that. Don't say much to me, but I know that they have lots of difficulties dealing with those natural boundaries.
Okay, I keep that in mind. Yeah.
I have a question, actually, a specific question. If you have American option, instead of hedging, you want to allow some shortfall and apply this machinery with risk measures. So how it works?
I don't know yet. Yeah, that's certainly something which would be interesting to look at.
Next time.
Yeah.
Okay, thank you.
Okay, thank you for listening.